apologies for being late, but let's get started. The very first talk is called LLOR, Automated Repair of OpenMP Programs. It will be given by Utpal Bora. Go ahead. Thank you.
Thank you, Sriram. Am I audible? Okay. So I'm Utpal Bora. Today I'm going to present our work, Automated Repair of OpenMP Programs. So this work is mainly from Gautam Muduganti, but because of visa reasons, he is not able to be here. So I'll be presenting our work on his behalf. So we all know about parallel programming. If we have a big enough problem, we want to use the multi-cores that we have nowadays, and we want to break down the big problem into smaller chunks, and each smaller chunk can be processed by different processing elements. So there are different models of parallel programming. So what we have tried is like OpenMP is one of those, which is shared memory parallel programming. That means all the processing elements will be sharing a common memory, and it supports two programming models, SIMD and MIMD. In SIMD programming model, as we know, all the instructions are same. The same instruction is executed by all the processing elements, but the data is shared or mapped from the shared memory. Then for the for the MIMD model, OpenMP also supports MIMD model where you have like different set of instructions that are assigned to different processing elements, and all the processing elements will work on different data in the shared memory. So as we all know, parallel programming is good, it is beneficial, but it has its own quirks. So one thing is like one problem that we generally face with data races. So data races are a common set of bugs in parallel programming, where mostly with shared memory parallel programming, where if we have more than two threads trying to access the same memory location, and one of the accesses is a write operation, but the accesses are not protected by any locks or any order, then we might have something called data races. So in OpenMP, let's see how we can have data races. So OpenMP is a pragma directed. So so basically we provide pragmas to C, C++ or Fortran programs to define a parallel region. In this example, we have a parallel region which is defined by pragma OMP parallel construct. So all the statements inside this construct will be executed by all the threads that participate in the parallel region. So here there's a concept of shared memory and private memory. All the threads in OpenMP, they have two views of memory. One is the shared view, one is the private view. The private view, so there the private variables are stored in private view of the memory, and the shared memory is basically shared among all the threads. In this example, we have like data is a shared variable, or data is a shared array that is that all the threads have access to, and we have like the other variables like temp and thread ID that are thread private. So that will not, like the data races basically occur only on the shared variables, not on the private variables. So in this example, what we can have is like, let's say there's a input array, and this array is basically the data array, and we might have like different execution sequence or execution trace of this program. So let's say we consider two threads, thread 0 and thread 1. Thread 0 has like, let's say in this sequence, thread 0 reads the element first and followed by thread 1, and thread 0 writes first and followed by thread 2. So we have the output data array after this execution. We can also have a different execution sequence where thread 1 first reads and writes to the array. Now thread 0 reads the new value of the from the array. So we have a different data, which is basically, we can have different outputs from the same segment of code. So this is basically the data race that we have in OpenMP programs. And there are some cases where we can have corrupt data as well, where the writes and reads happen simultaneously. If the operation is not atomic, we might have data that is corrupt. So to mitigate this, we have, so what we do is we introduce barriers. So these barriers are a construct in OpenMP basically synchronization constructs, which forces each thread that are participating in the shared region, parallel region. So what it marks is basically all the threads should wait at this barrier before they can proceed forward. So in this example, all the threads can read from the data array, but it has to wait before any thread can write to memory location, shared memory location. So this avoids the issue that we had before. So this is how we will try to mitigate the data races in the program automatically. There is one more construct that is very popular, which is called OpenMP work sharing construct. In this example, we can see that there's a pragma OMP parallel for, which should always be followed by a for loop. So basically, this pragma is on top of the for loop, which divides the iterations of the for loop among the threads, participating threads. So the statements are pretty similar to the previous example. Here also, data is shared, and temp and variable I is private to the threads. So we can have same issue as different outputs. So one difference between the previous one is that we cannot insert a barrier inside the OpenMP parallel for construct. So what we need to do is we use a different pragma called pragma OMP ordered. So which basically states that all the statements inside the ordered construct should be executed in the sequential order, in the program order by all the threads. So this way we can prevent any data races. So, so with this, let us see the goal. So the goal of our work is basically given a program which has data arrays, can we generate a program that like automatically corrected program which do not have data races and which has minimal number of barriers or synchronization constructs. So, so this is the architecture of LLOR. We can have OpenMP programs in C, C++, and Fortran. So we use the clang and flang front end to generate LLVM-IR. So we compile to LLVM-IR. And LLOR has two components. The first component is instrumentation phase, and the second component is a repair phase. So the instrumentation component basically finds the OpenMP constructs in LLVM-IR, and it annotates some metadata into the IR, and it introduces some variables called barrier variables that I will discuss later. Once we instrument the IR, the repair candidate takes over. So the repair generator candidates basically reads the instrumented IR, and it queries the verifier. Here, verifier is a data race detector, which acts as an oracle for our exercise. So in this case, we use LLOV, which is a state-of-the-art data race detector for OpenMP programs. And LLOV reports the data races if there are any, and it reports the source location where the data race occurs. So in the next phase, what we do is we analyze the data races from the oracle, and using these data races, we form some clauses that I will discuss later. So these clauses, we send it to a solver. In this case, we use Z3 for our purpose. And if the solver says that the clauses are not satisfiable, we say that the program cannot be repaired. But if, let's say, if there's a solution exists for the clauses, what we do is we send it to the repair candidate again. The repair candidate takes the solution and enables those barriers and generates a new repair candidate, which it sends to the OpenMP verifier. Then if LLOB reports that there are no data races, we say that the program has been repaired, and we generate the source location where the barrier should be placed to fix the program. And we also generate the correct program in LLVM-IR, which can be compiled.
So you're fixing the source, not the LLVM, or both the LLVM and
we mostly fixing the IR at the IR level, but we also generate that at this source location we can put a barrier. So, yeah. So this repair candidate, these components, written in .NET C#, and the first component instrumentation phase is in LLVM in C++. So together we have the tool LLOR. So this is not new to use this type of counterexample driven approach to repair programs. Like we use LLOB as a oracle, but we are not dependent on LLOB. We can use any other data risk detector as verifier. Yeah, it should not be difficult to change the verifier. It should be straightforward. So let us take some examples how the algorithm works. I'll consider two examples. One is for parallel region, and the other is for work sharing for construct. So this is a parallel region where we have 4 statements. All the 4 statements will be executed by all the threads that are participating in the parallel region. And we have 4 memory accesses to the shared memory. Data A and data B are the arrays that are shared among all the threads. So the instrumentation phase will go through this in the LLVM IR. It will pick the locations where the shared memory accesses happen. So we have the 4 locations, and we introduce Boolean variables as we call them barrier variables. We introduce one barrier variable for each shared memory access, either it is read or write, and we send it to the repair candidate generator. Because all the Boolean variables are false, the repair candidate generator will not introduce any barriers into the program, and it will send this program to the verifier. The verifier reports that there is a data race between the statement 1 and statement 3 due to read and write to the same memory array. And so at this stage, the clause generator kicks in, where we try to read the error message from the verifier, and we read between these 2 locations, we read all the memory accesses that happen to the shared memory. In this example, there's a read access to at B2 and B3. So we say that if we place a barrier at B2, we can avoid the data race, or we can place that at B3.
So in this case, when you do the verification,
yes.
Is your verification just looking at an access into the array, or do you also look at what indices you are accessing? So in other words,
yes.
If I change that ID plus 1 to that ID, you may not have a data race.
So the verifier does look into the array accesses. In this case, LLOB does verify the actual array accesses. So then we send this clause to the solver, which is Z3 for this case, and we can either satisfy it with B2 or B3. Let's say we pick B2, and then the repair generator candidate generates a new candidate by inserting a barrier before B2, right? And then it sends the same program to the verifier LLOB, in this case LLOB, right? So LLOB reports that there is one more bug, and at this stage, the clause generator accumulates all the clauses it has seen till at this point. So B2 or B3 was there before, and we see that there is a data race from statement 3 to statement 4, so, but there is a shared memory write at B3. So we add one more clause B3 or B4, because we can add a barrier before B3 or before B4. So with this, then we send it to the solver again, which solves B3, satisfied both the cases. So if we set B3 to true, that means we introduce a barrier before B3 and send it to the verifier. This time verifier detects that there are no data races. So at this point, we have repaired the program, and we correct the program in LLVM IR, but we also generate the source location where the barrier should have been put. So this is in context of parallel region. Let me take the example of work sharing for construct, where we have a for construct. It is different because we cannot put a barrier inside a for construct. So the example is very similar. We have all the barrier variables. Let's say we have the same clauses. So once we know where once we know where we should put the barrier, B3 is in the case. So what we do is, instead of putting a barrier, we put a ordered construct from the point where it should be put to the last memory access, shared memory access, or last access where it produced the data is. So since OpenMP worksharing construct only allows one such ordered clause within that body, so it might happen that we might have multiple instructions inside the ordered clause, and some of the instructions might not be accessing shared memory. So it is a limitation. But yeah, so this solves the data race issue that we have. So going into the strategies, we apply two strategies in solving finding the solution to the problem. So first one is maxset. We use maxset to solve it. Let's say we have 5 data races in the program, and let's say there are 6 memory accesses, shared memory accesses in the program. So if we have 6 accesses, we will have 6 Boolean variables or barrier variables, and we create the hard clauses based on each data race. So basically, within the data race, whatever shared elements are there or shared memory accesses are there, all those variables will be part of that particular clause. So in this case, we have 5 clauses, and the soft clauses are basically to minimize the number of such barrier variables we want to put. So yeah, the hard clauses must be satisfied. Soft clauses need not be, but we try to maximize them. The other strategy is using a minimal hitting set algorithm, where this is a polynomial time greedy algorithm that we try to maximize, satisfy as many clauses as possible with minimal number of literals. Let's say with the same set of examples, like 5 clauses, if we set B2 to true, we satisfy first 3 clauses. If we set B6 to true, the next 2 are satisfied. So basically, we have a solution. So why it is useful is because maxset is costly. So we try to, because we might go for multiple iterations over generating different repair components. So instead of using maxset every time, we use MHS, and but MHS need not produce the best optimal solution. So once we have,
So you would never have a negation in any of your clauses, right?
no, yeah.
Does that affect anything?
I'm not quite sure about it. I'm not expert in this area, so probably not, I think. But yeah, we will not have any negation. And yeah, so if once we get a solution from MHS, we send a query to maxset to find the optimal solution, and we generate the repair candidate and produce, also highlight the source location where it should be placed in the high-level code. So having said that, we did some benchmarking. We used a few OpenMP open source benchmarks. There are quite a few. Like data race bench is a popular benchmark in data race detection community, where there are multiple C, C++ kernels and Fortran kernels with and without data races. We know that there are some data races in these programs. And we also use some exascale projects, these are HPC applications. These are big applications that we tried. And we also use Rodinia and parallel research kernels. And we also designed some of the smaller test cases. And for our experimentation, we used LLVM 12, and we use classic Flang, which is little bit different from, which is basically different from the current Flang that is there in LLVM. And we used the verified LLOV version 0.3. So since this is the only tool that we know of that can repair OpenMP programs, we do not have any comparison with any other tool. So we categorize our results into 3 categories, basically. First one is when we have no data races in the program, or the verifier says there are no data races in the program. In that case, what we do is, like for 70 out of the 75 C++ cases, 71 are not repaired by the repair tool, but 4 of them are repaired. This can be either because of 2 things. First one is that it optimized or it reduced some of the synchronization constructs, and without those synchronization constructs, also there is no data race. And the second thing can be that so it is that basically for a Fortran programs, there is a case where the verifier generates false negatives if we remove some of the barriers from the program. So this is to do it mainly because Flang and Clang does not generate same source code for similar programs. So I think it is an engineering issue that we have reported. So basically because of that, some of the programs are like LLOR suggests that we should repair them because that is the optimal solution without like having extra barriers. The next category is like where we actually have data races. These are the ones that we care about. So out of 117 C++ programs where we have data race and the verifier reported data race, we could fix 92 of them correctly. And out of the 30 Fortran kernels, we could fix 15 of them with the strategy of inserting a barrier and putting the order clause. However, we could not repair 5 of the C++ kernels because they were not able to, like, it is not merely possible to just fix the issue with a barrier or a synchronization construct. We might need a critical section or something more complex. And there are like some cases where the program's timed out, where we set a timeout of 300 seconds. And some of the constructs are unsupported right now by LLOR because we repair only parallel construct and work sharing constructs. So there are other constructs like SIM deconstruct and GPU offloading constructs that should be fixable. Like there can be extensions to LLOR that can target those. So the last category is basically where the verifier does not support the OpenMP constructs, and there are like 43 C++ kernels and 21 Fortran kernels, either because there are complex features like teams construct or I can't recall. So yeah, there are multiple constructs that are not supported by the verifier. Probably if we have used a different verifier, those could also be supported, and LLOR could have detected or modified the source program. And some of them had compiler issues, like 10 of them. This is because the Flang version that we used is not part of LLVM. It is classic Flang, and it is not feature complete. So some of the OpenMP pragmas were not supported in Fortran. So the recent Flang that we have in LLVM, like at the time, Flang was under development, so it could not generate LLVM IR. So it was generating ML IR and then generating like doing code generation directly, but there was no LLVM IR generation at that stage. So we had to use classic Flang for that. Yeah, there are plans to switch to like using the recent version of Flang, which should be able to generate LLVM IR, and some of the issues that we have should go away because these are engineering challenges. And the verification errors at last are due to timeouts from the verifier, like the verifier timed out for 6 of those cases. And yeah, with that, our tool is open source. Please go ahead and try it out. Our paper is available on arXiv, and the artifact is also available on the archival repository Jnodo. And we have received all the 3 badges from Artifact Evaluation Committee. With that, thank you for your time. Yeah. if you have any questions.
Questions?
Interesting work. I was wondering, like, did you do performance analysis of, the programs? Because you could imagine different solutions where you could put a barrier here or you could put a barrier there, and one of them just happens to, reduce all the parallelism, and the other one keeps it. So they would both be free of data races, but clearly you would want the one that was more parallel. So
Yeah,
did you do those kinds of
no, and yeah, we didn't try that. Yeah, this is a very good suggestion. We should have tried that. Yeah, I think we can optimize that a bit really.
So following up on Kedar's, so not every program, every data race is barrier fixable, right?
Yes.
You have to be able to do data race free execution in lockstep.
Yes.
That's the only case where you can introduce barriers to fix it, if I'm not mistaken.
Like not exactly that. In terms of OpenMP, let's say if we have a write operation to the same memory location, and both of them are overriding the same memory location, in that case, a barrier would not fix it. Maybe we need a we need a lock basically to protect, or we need a order clause that we shown where like the thread executes based on their ID, the lower ID threads execute first, so on and so forth. So yeah, I think we can like fix some of these cases with these constructs, and there are like other synchronization constructs in high-level synchronization constructs in OpenMP that I think internally uses similar locking mechanism.
Thank you. Any other questions? Oh, yeah, Gautam.
I guess the question is, I can imagine a programmer could write their program in such a way that it creates a huge number of barriers, but if they had reordered their statements, it would be equally correct. Is there any sort of extension to your work that might reorder what they've written in order to get a more optimal set of barriers?
You mean like program transformation in terms of like optimizing the sequence or order of the shared memory accesses? No, we have not tried that. So it was mostly in terms of verification and like reducing the synchronization constructs.
So even removing existing barriers would be a good idea.
Yes.
If they put in a barrier, maybe it's not needed, you could use the same framework to remove it. That would be great.
Yes, precisely.